We have lecture 4 of Jason's modeling the evolution of populations with selection.
Okay, thank you, and welcome back to the 4th of 5 lectures in this series. The slides aren't advancing. So recall that last week we were discussing branching Brownian motion with absorption. We begin with some configuration of particles on the positive real line. Each particle independently moves according to standard one-dimensional Brownian motion with a drift to the left of rho. Each particle independently splits into 2 at rate 1, and particles are killed if they reach the origin. Now, we were interested in this process partly because it could be used as a model of a population undergoing selection. And in that framework, we think of the position of each particle as corresponding to the fitness of the individual. And then the absorption at 0 is modeling the deaths of individuals whose fitness gets too low. Last week, we mentioned this result from Harry Keston's original 1978 paper on branching Brownian motion with absorption. And Keston showed that branching Brownian motion with absorption dies out almost surely if the drift to the left is greater than or equal to the square root of 2. But if the drift to the left is strictly less than the square root of 2, then the process survives forever with positive probability. Now, in the second lecture last week, we considered the supercritical case where the drift was strictly less than the square root of 2. And we considered the case of subcritical drift where the drift was greater than the square root of 2. In the third lecture, we considered the case when the drift was just slightly supercritical, so slightly smaller than the square root of 2. And that turned out to be the most relevant case for modeling a population whose size was approximately stable over time. And we showed that in that case, the size of the population evolves over time like Nevers' continuous state branching process, and the genealogy of the population could be described by the Bolthausen-Snettman coalescence. Now, in this lecture, we're going to consider the one case that we have not yet considered, which is the case when the drift is exactly critical. So rho is equal to the square root of 2. And we will see that some of the ideas that were developed to study the slightly supercritical case, along with some additional tools, can be used to improve upon some classical results for this process. And so we're going to focus mostly on 2 questions. First, what is the probability that the process survives for an unusually large time t? So it's the critical case, so we know that the process will eventually die out, but we want to know what's the probability that it survives for an unusually large time. And then second, conditional on the event that the process survives for an unusually large time t, what does the configuration of particles look like at time t? And results like this are known as Jaglon type limit theorems, after the result of Jaglon that describes the behavior of critical Bienemay, Galton, Watson processes conditioned to survive for a long time. And then also in the second half of this lecture, we're going to return to the second of the 2 population models that I introduced at the end of the first lecture. So we're considering branching Brownian motion with the critical drift of the square root of 2. And so that you'll have a sense of where we're going, I'm going to jump right in and state what I consider to be the main results, although I will state more precise versions of these results as well as additional results later on. So remember that n of t denotes the number of particles at time t, and we're going to let zeta be the extinction time. So the first time that the process has gone extinct. So now Keston proved this result about the long-run survival probability for the process. So Keston showed that if we start the process from 1 particle at x at time 0, then the probability that the process survives for a large time t is bounded above and below by these 2 quantities. So we can see that the probability that the process survives for time t looks a lot like x times e to the root 2x minus 3 pi squared t to the 1/3 power. However, the upper and lower bounds differ by more than a constant factor because of these e to the plus or minus k log t squared terms which show up. So here then is the new result, which is sharper. And this result, like most of the results that I will state in the first half of this lecture, comes from joint work with Pascal Maillard. And this result says that if we start the process from one particle at x, then the probability that the process survives for at least time t is asymptotically some constant times x times e to the square root of 2x minus 3 pi squared t to the 1/3 power, where by this symbol here, I mean that the ratio of the two sides is tending to 1 as t goes to infinity. Now, I should mention that Derrida and Simon obtained this result more than 10 years earlier using non-rigorous methods. And also in earlier joint work with Julian and Nathaniel Beresticki, we obtained upper and lower bounds for this survival probability that were correct up to multiplicative constants. One other thing that I want to mention here is that in the paper with Pascal Maillard, we considered a slightly different scaling where particles branch at rate 1/2 instead of at rate 1. And that scaling is nice because it eliminates a lot of the square root of 2 factors that are going to show up. But to keep consistent notation throughout these lectures, I've translated the results to the setting that we've been working in where particles branch at rate 1, which is a fairly simple scaling. But the results do look a little bit different in the paper. Now, we also have a result about the behavior of the process conditioned to survive for an unusually long time. Again, n of t is the number of particles alive at time t, and we'll denote by r of t the location of the rightmost particle at time t. So that's the particle that's furthest from the origin. And then Keston showed that if we start with one particle at x and condition the process to survive for at least time t, then the probability that the number of particles at time t is greater than e to the k1 times t to the 2/9 times log t to the 2/3 is going to 0 as t goes to infinity. And likewise, he showed that it is asymptotically unlikely that any particle at time t will be above some constant times t to the 2/9 times log t to the 2/3. So we're now able to prove a sharper result, which tells us that these log t to the 2/3 factors are unnecessary. The logarithm of the number of particles at time t and the location of the rightmost particle at time t are both of the order t to the 2/9. And more precisely, if we start from one particle at x and condition on the event that the process survives past time t, then t to the minus 2/9 times the log of the number of particles at time t, and t to the minus 2/9 times the position of the rightmost particle at time t, both converge in distribution to a cube root of an exponential random variable. Now, just as in the slightly supercritical case, to study this process, we're going to need to make first moment calculations to understand the typical behavior of the process, and second moment calculations to control the fluctuations. And also, just as before, these moments are dominated by rare events in which one particle moves unusually far to the right and then has an unusually large number of descendants that are able to survive. And so to understand the typical behavior of the process, we need to apply a truncation argument. Now, one way to apply truncation, which we discussed before, was to fix some large positive number L and then kill particles that reach either 0 or L. And so this leads to branching Brownian motion in a strip. And we saw last time that the density for branching Brownian motion in a strip can be approximated by this expression here. So this means that if we start from one particle at x, then the expected number of particles in some set A at time t is well approximated by the integral of this expression here over the set A. It turns out, however, that in this case, we will not get sharp enough truncated moment bounds if we kill particles at some fixed level L. And the reason for that is that in the critical case, the number of particles is decreasing over time as the process moves towards extinction. We can see that from the e to the minus pi squared over 2L squared times t factor that appears in the density formula for branching Brownian motion in a strip. And so we're going to need to move the right boundary closer to the origin over time as the number of particles decreases. So what we'll do is, so we can fix some positive number t, and we can define this constant c, which happens to be 3 pi squared to the 1/3 over the square root of 2. And then we're going to let L sub t of s be c times t minus s to the 1/3 power for s between 0 and t. And we're then going to consider branching Brownian motion, in which at time s, particles are killed both at the origin and at Lt of s. And this upper boundary was already considered in this original paper by Keston. So the way we have to think about this is that we have to set the time t to be roughly when we expect the process to go extinct, based on what the initial configuration of particles looks like. And then the significance of this curve Lt of s is that very roughly, a particle that gets very close to L sub t of s at time s has a good chance to have descendants alive in the population at time t. Now I want to say a bit more about where the formula for this right boundary is coming from. So roughly the number of particles at time s is decreasing according to this differential equation here. Now, of course, this is very rough because the number of particles is quite random, but on average, because of the e to the minus pi squared over 2L times t factor that appeared in the density formula, very roughly, the number of particles at time s is decreasing at a rate of minus pi squared over 2Lt of s squared times n of s. Now, we also saw from the slightly supercritical case that the best place to put the right boundary is roughly at 1 over the square root of 2 times the log of the number of particles. And so if we differentiate the right-hand side here, and then substitute in this expression that we just obtained for the derivative of the number of particles at time s, we arrive at a differential equation for Lt of s. And furthermore, we want to set L sub t of t to be equal to 0, because we think of L sub t of s as being where a particle needs to get to at time s to have a descendant alive at time t. And a particle anywhere at time t is going to have a descendant alive at time t. And so just solving this differential equation then is what gives us this formula for the right boundary at Lt of s. Now, it's harder to estimate the density when the right boundary is moving. However, some results in this paper of Matt Roberts, which built on earlier work of Novikov, do allow us to get an approximate formula for the density in this case. And because the right boundary is moving only very slowly, the density turns out to resemble the formula for branching Brownian motion in a strip, but with Lt of 0 and Lt of s in place of L. And so, again, following an approach very similar to what we used in the slightly supercritical case, we're going to analyze this process in the following way. So we're going to stop particles which reach L sub t of s minus a at time s, where a is a large positive number. And this will give us good control over the particles that stay below the boundary. The number of such particles will stay relatively close to its expectation. But then after a particle reaches L sub t of s minus a, we'll follow the descendants of this particle along until they reach L sub t of s minus a minus y for large y. And then we'll reincorporate those descendants back into the process. And using again the result of Neveu that we stated last time, a particle that reaches L sub t of s minus a will have m of y descendants that reach L sub t of s minus a minus y, where m of y is approximately y to the minus 1 times e to the root 2y times this random variable w, and the probability that w is greater than some large number x is asymptotically a constant over x. So now if we fix a positive number t, we can define for s between 0 and t this expression z sub t of s. So here we're taking a sum over all particles at time s, and a particle at the location x is making a contribution to this sum, which is proportional to e to the square root of 2 times x times the sine of pi times x over the right boundary L sub t of s. And it turns out that this is going to give us a fairly good measure of the size of the process at time s. That contribution that we assign to a particle at x is coming from the density formula, which tells us roughly how much we expect that particle to contribute to the process at future times. The multiplication by LT of s times e to the minus root 2 LT of s here is just scaling. And we multiplied it by this indicator to keep the sign from going negative. And so we're only considering particles that are below the upper boundary. And so now as t goes to infinity, under suitable initial conditions, these processes zt will converge to a limit process. And this limit will be a process with jumps, where the jumps occur when one particle moves unusually far to the right and has a large number of descendants that are able to survive. Now, when a particle does reach LT of s minus a, then its contribution will be roughly proportional to the number of its descendants that reach LT of s minus a minus y, which is going to be proportional to the random variable w on the previous slide. And therefore, jumps of size greater than x will occur at a rate proportional to 1 over x. And the jump rate will also be roughly proportional to the size of the process at time s. So once again, we see that the jump rates should be matching the jump rates in Naviers' continuous state branching process. And we can summarize that here in a precise limit theorem. So we assume that zt of 0, that's our measure of the size of the process at time 0, converges in distribution to some limit random variable z. And that's typically going to mean that the initial configuration of particles will depend on t. We'll also assume that LT of 0 minus the location of the rightmost particle at time 0 converges in probability to infinity. So this means that the rightmost particle at the initial time starts out well below the right boundary at LT of 0. And then the finite dimensional distributions of these processes zt converge as t goes to infinity to the finite dimensional distributions of Naviers' continuous state branching process with branching mechanism a times q plus 2/3 q log q. So it's the same limit process that we saw in the slightly supercritical case, but one thing to notice here that's different is that we have a time change, which is mapping the interval from 0 to t on the time scale of the branching Brownian motion to the entire positive real line on the time scale of the continuous state branching process. To explain where that time change is coming from, we saw in the slightly supercritical case that particles were hitting the right boundary at a rate proportional to log n to the minus 3. We had that log n cubed time scale, and that's also a constant times L to the minus 3. And so in this critical case, we would expect that at time s, particles should hit the right boundary at LT of s at a rate proportional to LT of s to the minus 3, which is proportional to 1 over t minus s. And so if we want to get a time homogeneous process in the limit, if we use u to denote the time for the continuous state branching process, then the rate du at which time is moving forward needs to be proportional to 1 over t minus s. And so solving this differential equation, we get that u should be the log of t over t minus s. And then rearranging, we see that time u in the continuous state branching process corresponds to a time of 1 minus e to the minus u times t in the branching Brownian motion. And so in particular, the behavior of the branching Brownian motion near time t is matching up with the large time behavior in Naviers' continuous state branching process. So with that in mind, it will be useful to review some asymptotic results for Naviers' continuous state branching process. So let's let x be a continuous state branching process, which starts at little x, and it has branching mechanism a times q plus 2/3 q log q. And then some early results of Gray on continuous state branching processes tell us that this continuous state branching process never goes extinct and does not explode in finite time. So the probability that x of u is strictly between 0 and infinity at all times is equal to 1. Furthermore, if we let alpha be e to the minus 3a over 2, then this continuous state branching process started from x approaches infinity as time goes to infinity with probability 1 minus e to the minus alpha x, and the continuous state branching process converges to 0 with probability e to the minus alpha times x. And the way we can think about this result is that the continuous state branching process at time 0 may include a certain number of so-called prolific individuals whose number of descendants at time u tends to infinity as u tends to infinity. And it turns out that the number of such prolific individuals has a Poisson distribution with a mean of alpha times x, and that's going to lead to these two probabilities. And because of the connection between branching Brownian motion and Nevers' continuous state branching process that was summarized on the previous slide, the survival of the branching Brownian motion until time t roughly corresponds to the event that the continuous state branching process diverges to infinity. And so we're now in a position to state our result about the long-run survival probability for branching Brownian motion. So we're going to assume for simplicity that the initial configuration of particles at time 0 is deterministic, but it may depend on t. And recall that zeta denotes the time when the process goes extinct. So let's suppose first that zt of 0, that's our measure of the size of the process at time 0, converges to some limit z. And we'll also assume that lt of 0 minus r of 0 converges to infinity. So no particle can start out too close to the right boundary. Then the probability that the process survives for at least time t converges as t goes to infinity to 1 minus e to the minus alpha z. And that's just coming from the corresponding result for the continuous state branching process started from z. Now suppose instead zt of 0 goes to 0. Well, then this result tells us that the probability that the process survives until time t converges to 0. But we can also be more precise. We can approximate in that case 1 minus e to the minus alpha z by alpha times z to get that the probability that the process survives until time t is asymptotically alpha times zt of 0, where this symbol here means that the ratio of two sides converges to 1 as t goes to infinity. Now, a special case of that result is if we start the process from just a single particle at x, and then we get that the probability of survival until time t is asymptotically a constant times x times e to the root 2x minus 3 pi squared t to the 1/3 power. That's the result that we stated earlier in the lecture. Before we had an arbitrary constant in front instead of the square root of 2 times alpha times pi, but this is really the same thing because alpha depends on the unknown constant a from the branching mechanism in the continuous state branching process. Now we could also consider what happens if we start at time 0 from one particle at L sub t of 0 plus x, and then we fix x while letting t go to infinity. In that case, the survival probability until time t, the probability of survival until time t, converges to some function phi of x. Phi of x goes to 1 as x goes to plus infinity. Phi of x goes to 0 as x goes to minus infinity. And in between, we don't have an explicit formula for phi, but we know that it satisfies this second order differential equation here. So what's going on in this case is that if we start with one particle that's close to LT of 0, there's going to be some randomness in the initial stage of the process that's determined by the limiting value of the derivative martingale. And so this survival probability is actually the survival probability for the continuous state branching process, but started not from a fixed point, but instead from this random point that's given by the value of that derivative martingale. Now, from this result, we can also obtain an asymptotic result for how long the process survives past time t, conditional on the event that it survives for at least time t. So let's assume that zt of 0 is converging to 0, so that survival until time t is unlikely. And again, we assume that no particle starts out too close to the right boundary. And then conditional on the event that the process survives past time t, or survives until time t, the amount of time past time t for which the process survives is of the order t to the 2/3 power. And more precisely, t to the minus 2/3 power times zeta minus t converges in distribution to an exponential random variable. And the proof of this result is sufficiently simple that I chose to sketch it here. So we want to calculate the probability that the process survives for at least time t plus y times t to the 2/3, given that it survives for at least time t. We can write this conditional probability as the ratio of these two probabilities. And then the result on the previous slide tells us that the numerator is asymptotically alpha times z sub t plus y z plus yt to the 2/3 of 0. And likewise, the denominator is proportional to zt of 0. And just from the formula for zt, one can calculate that as long as no particle starts out too close to the right boundary, the ratio of these two expressions is converging to e to the minus √2 times cy over 3. And that's why we end up with this exponential distribution in the limit with a mean of 3 over the square root of 2 times c. So now finally, we're able to state our Jaglon type limit theorem for the behavior of the process at time t, conditioned on the event that the process survives until time t. Now, the key idea behind this Jaglon type limit theorem is that we need to think about what the configuration of the particles should look like at time t if the process is eventually going to die out at time t plus s. So first of all, notice that if the process will go extinct at time t plus s, then z sub t plus s of t should not be too close to 0 and should not be too close to infinity. If z sub t plus s of t is very small, then the process will most likely die out well before time t plus s. If z sub t plus s of t is very large, then the process will most likely survive well beyond time t plus s. So z sub t plus s of t should be basically of order 1, neither too small nor too large. Also, by time t, the process should have had a chance to, the configuration of particles should have had a chance to settle down into kind of a stable limiting configuration. And so the density of particles near y should be proportional to e to the minus √2y times the sine of pi y over L sub t plus s of t. That's coming from the density formula that we stated before. And this means in particular that the rightmost particle should be reasonably close to the right boundary at L sub t plus s of t, which is c times s to the 1/3 power. And then a short calculation tells us that if we put down approximately this number of particles according to this density, then that is what it's going to take to make z sub t plus s of t roughly order 1, rather than much smaller or much larger. And consequently, the log of the number of particles at time t should be approximately the square root of 2 times L sub t plus s of t. Now, we've just seen that conditional on the event that the process survives until time t, we expect the process to survive for an additional t to the 2/3 times v time units, where v has an exponential distribution. So the position of the rightmost particle at time t should be approximately, well, what we have to do is to plug in t to the 2/3 v in place of s. So the location of the rightmost particle at time t should be approximately c times t to the 2/3 v to the 1/3 power. And that's c times t to the 2/9 times v to the 1/3. And we get something similar for the log of the number of particles. And so this leads us to the following limit theorem. Let's assume that zt of 0 converges to 0, so that survival until time t is unlikely. We assume that no particle starts out too close to the right boundary. And then conditional on survival until time t, t to the minus 2/9 times the log of the number of particles at time t, and t to the 2/9 times the position of the rightmost particle at time t, both converge in distribution to the cube root of an exponential random variable. And furthermore, it's the same exponential random variable that determines how long the process survives beyond time t. So we have the joint convergence of these three random quantities. So finally, I want to state just one more result about this process. One can also ask, conditional on the survival of the process for an unusually long time t, what can we say about the behavior of the process before time t? So again, we're going to assume that zt of 0 goes to 0, so that we are unlikely to survive until time t, and no particle starts out too close to the right boundary. And then one can show that the finite dimensional distributions of these processes zt under the same time change that we looked at before converge as t goes to infinity to the finite dimensional distributions of Navière's continuous state branching process started at 0 and conditioned to go to infinity. Now, it's not immediately obvious what that means, because if you start a continuous state branching process at 0, it stays at 0. But what we can do is to start the process from some positive number s and condition it to go to infinity. And then the law of that process has a limit as x goes to 0. And that's the law that we're referring to. And we can interpret that limit as the process that keeps track of the number of descendants over time of a single prolific individual at time 0. This is actually all I want to say about branching Brownian motion with absorption. We've now studied all 5 of the cases that I outlined at the beginning. I'm going to make a substantial shift in topic now, and we're going to start to, we're going to return now to the second of the 2 population models that I introduced at the very end of the first lecture. Yes, that's a good idea.
So can you deduce the genealogy from this result?
Can we deduce the genealogy? We almost certainly could. It should follow by the same method that was used in the slightly supercritical case. We didn't actually go through that. It didn't seem so exciting because we already had it for, almost the same process. But yes, I do believe we could deduce the genealogy for this process. And you would see the Bolthausen-Snittman coalescent once you untangle the time change.
Yeah, so this would require more work. That's what you say. It's probably the same techniques, but it's not. There is no kind of.
It's not. Yeah, it would require a little bit more work. I think the same argument that we used in the slightly supercritical case would carry over pretty much without change. I didn't check that carefully, but I don't think I don't think new ideas or substantial new ideas anyway would be needed. Was there?
Yeah, I wanted to ask just, it's probably kind of technical question, but to get the conditional law when you start at 0 for the continuous state branching in this setting, does that arise as a probability measure, or do you have to kind of, is there an excursion measure in here somewhere or a canonical measure kind of thing?
No, it's a probability measure because the law of the continuous state branching process started from x. I mean, that's a probability measure, right? That's a law.
Yeah.
Right, and so those laws have a limit as x goes to 0. So the point is that, remember that the continuous state branching process has at time 0 prolific individuals basically at rate alpha, right? So if you start from x, you have alpha times x prolific individuals at time 0, Poisson with mean alpha times x. And so as you let x go to 0, most likely you have no prolific individuals, but with a small probability you have 1. And so what you're really getting is just a legitimate probability law that describes the number of descendants over time of one prolific individual. Okay, so this is a review of the second population model that I had introduced previously. So we're going to assume that we have a population of fixed size n. Each individual independently acquires mutations at rate mu sub n. So mu sub n is the mutation rate per individual. So we get mutations at times of a rate mu sub n Poisson process. We assume that all mutations are beneficial. And we model that by saying that an individual that has J mutations at time t, which I'm going to refer to as a type J individual, has fitness 1 plus Sn times J minus M of t, where M of t is the average number of mutations of the n individuals in the population at time t. So if an individual has 3 more mutations than average, its fitness is 1 plus 3 times Sn. And this parameter Sn is measuring the selective benefit that one gets from a mutation. Now, each individual independently lives for an exponentially distributed time with rate 1. And when an individual dies, we choose an individual at random from the population with probability proportional to fitness to be the parent of the new individual. So individuals with higher fitness are more likely to give birth, and the new individual that's born, of course, has the same type as the parent. Now, there are some other variations of this model that appear in the literature. For example, Durrett and Mayberry studied this model, but they said that the fitness of an individual with J mutations is 1 plus Sn to the power J. Etheridge and Cuthbertson studied almost this model, but they said that an individual with K mutations replaces an individual with J mutations at rate 1 over n, as in the Morin model, if K is less than or equal to J, and at rate K minus J if K is greater than J. So these small differences in the formulation of the model should not really affect the main results that we're going to discuss, and I'm not going to explicitly mention these little changes when referring to previous results in the literature. Now, what we basically expect in models like this one is that the fitness distribution of the population evolves over time like a traveling wave. So let's suppose at some time t1, we record the fitness level of every individual in the population, and we plot those values in a histogram. So then we're going to see some distribution of the fitnesses of the individuals, something like this curve here. But then over time, as the population evolves, the fitness of the population increases, and so that at some later time, t2, the fitness distribution may be over here. And this idea of modeling the evolution of the fitness distribution by a traveling wave goes back at least to this 1996 paper of Simring, Levine, and Kessler. So we're going to be interested here mostly in 2 questions. First, how fast does the fitness of the population increase over time? In other words, what is the speed of the traveling wave? And second, what is the distribution of the fitnesses of the individuals in the population at a given time? In other words, what is the shape of the traveling wave? Now, a number of results in the biology and physics literature indicate that the traveling wave should have approximately a Gaussian shape. And I've listed here several references for that. Also, Simring, Levine, and Kessler in their original 1996 paper, as well as Neher and Halischek a bit more recently, argued that the shape of the traveling wave can be described using the Airy function. And we will see that these conclusions are not contradictory. Under a certain range of circumstances, the shape of the fitness distribution will be Gaussian near where the bulk of the particles are located, but the tails of the fitness distribution can be better described using the Airy function. I want to give a brief survey of what is known about this model, both at a rigorous and non-rigorous level. So the simplest case to think about is when the mutation rate is very slow. So suppose, for example, the selective advantage conferred by each mutation is some fixed positive number s that does not go to 0 with n, and the mutation rate is much smaller than 1 over n log n. So in this case, typically there will be at most 1 beneficial mutation in the population at a time that has not already spread to the entire population. Now we have these mutations at rate n, the number of individuals, times mu n, which is the mutation rate per individual. And then once one of these mutations appears, individuals with the mutation are going to die at rate 1 and give birth at rate approximately 1 plus s. And so the number of individuals with the mutation is going to move up and down like an asymmetric random walk. And standard calculations for asymmetric random walks tell us that with probability approximately s over 1 plus s, this mutation will spread to the entire population, which is an event known as a selective sweep. So basically, we're going to have approximately an exponential waiting time with rate n times mu n times s over 1 plus s until we see one of these selective sweeps. Then we'll have another independent exponential waiting time until the next selective sweep, and so on. So that's a fairly simple picture. But as soon as mutations happen faster, so that we can have more than one beneficial mutation in the population at a time, the analysis quickly gets surprisingly complicated. Now, Durrett and Mayberry considered the case in which, once again, the selection parameter Sn is a fixed positive constant s, but the mutation rate is a little bit faster. So the mutation rate is behaving like n to the minus beta, where beta is between 0 and 1. And they showed that if T sub j is the first time that some individual has acquired j mutations, then T sub j minus 1 over log n is converging in probability to some constant little tj. So basically it takes order log n time for each new mutation to appear. And this is telling us that the rate of adaptation, or the rate at which new mutations appears, is of order 1 over log n. Durrett and Mayberry were also able to calculate very precisely the distribution of the fitnesses of the individuals in the population at a given time. And they did observe traveling wave behavior. However, their mutation rates are still sufficiently small that the number of distinct types in the population at a given time is some fixed positive constant that does not tend to infinity with n. So they were not able to observe anything like a Gaussian shape for the fitness distribution. Now, another parameter regime that's been studied quite extensively is when the mutation rates are a little bit faster than those considered by Durrett and Mayberry, and when selection is still fairly strong. So this parameter regime was studied in depth in this 2007 paper by Desai and Fisher. And Desai and Fisher were able to describe precisely the evolution of the traveling wave. And in particular, they were able to precisely describe the fitness distribution of the population at a typical time. And then a few years later, Desai, Walczak, and Fisher studied the genealogy of the population, and they determined that it could be described by the Bolthausen-Stintman coalescence. In 2017, I carried out a rigorous analysis of this process, and I was able to prove rigorously some of the results in these earlier papers, including the result that the Bolthausen-Stintman coalescence describes the genealogy. Now, the assumptions that were required for these results are a little bit too complicated for me to want to state them here. However, the assumptions do hold if the mutation rate behaves like e to the minus log n to the power c, where c is between 1/2 and 1, and if the selective advantage Sn that one gets from a mutation is decaying to 0 faster than 1 over the square root of log n, but much more slowly than the mutation rate. So just to give you a flavor of that work, I'm going to state two theorems from that 2017 paper. So this one describes the speed at which the population acquires beneficial mutations. We're going to let An be 1 over Sn times the log of S over mu. That's the natural time scale on which to study the process. And we'll let Kn be the log of n over the log of S over mu. That turns out to be the natural scale for the number of mutations that individuals have. And so let's let m of t be the mean number of mutations of the n individuals at time t. So that, of course, is a random quantity. But then there's a deterministic function little m, such that if we fix a time t that's different from 1, then the number of mutations at time a sub n times t, scaled by k sub n, converges in probability to this deterministic quantity little m of t. Now, little m of t over t is converging to 2 as t goes to infinity. And so the rate at which new mutations are taking hold in the population is given by 2 times kn divided by this time scaling parameter an. And after substituting in these values for an and kn, one gets that new mutations are appearing at roughly the rate 2s times the log of n divided by the log of s over mu. And Desai and Fisher and Ruzin, Brunet, and Wilk had also obtained essentially equivalent expressions for the speed of evolution using non-rigorous calculations. Now, we can also say something about the fitness distribution of the population at a typical time. Recall that if f is the density of a random variable that has a normal distribution with a mean of mu and a variance of sigma squared, then the logarithm of f of mu plus L over f of mu is minus L squared over 2 sigma squared. And so now to see something like a Gaussian shape in this model, let's let xj of t be the number of individuals with exactly j mutations at time t. And then we're going to examine the population at a certain sequence of random times tj. And we think of these times tj as representing the time when the number of individuals with j mutations is at its maximum. So then this result says that if we fix a positive number epsilon and an integer L, then as n tends to infinity, we have this limit result here. So on the left-hand side, we're considering the number of individuals of type J evaluated at time Tj, and we are comparing that to the number of individuals with J plus L mutations. And the theorem says that the logarithm of this ratio is very close to minus L squared times this expression here. And that's giving an indication of the Gaussian shape for the fitness distribution. Now, the variance of the implied Gaussian distribution works out to be 2 log n divided by the log of s over mu squared. And that's actually going to 0 under the assumptions of this theorem. So the fitness distribution is not actually converging to a Gaussian shape. It's converging to a point mass because one type in the population is dominant. Nevertheless, we do see Gaussian-like tail behavior with the L squared showing up here. Yes, they are stopping times, yes. Now, another case that one can consider is the case where we have strong selection and very fast mutation rates. So you, Etheridge, and Cuthbertson considered the case where both the selection parameter Sn and the mutation rate mu(n) are fixed positive constants that do not go to 0. And they showed that if m of t, as before, denotes the average number of mutations of the n individuals at time t, then the expected value of m of t divided by t is much larger or rather is larger than the log of n raised to the power 1 minus delta. So in particular, the rate at which mutations are being acquired in the population is tending to infinity as n tends to infinity. And a bit later, Michael Kelly obtained a corresponding upper bound for the speed of evolution of the order log n over log n squared. At this point, I've focused mostly on the case where we have strong selection, or at least relatively strong selection, so that the selection parameter Sn is fairly large. And in this case, the process has a sort of discrete flavor where individual beneficial mutations have a significant effect on the evolution of the population. And we have to keep track of these individual beneficial mutations in order to study the process. What we're going to focus on mostly, however, in these lectures is the case when the mutation rate mu(n) is large, but the selective benefit conferred by each individual mutation is small. And so in this case, we want to understand in particular the shape of the traveling wave that describes the fitness distribution of the population. Now, this idea that the individual beneficial mutations should have only a small effect on fitness is related to the so-called infinitesimal model in population genetics, which in some sense goes back more than 100 years to the work of Fisher in 1918. Barton, Etheridge, and Weber recently did some mathematical work on this process, as well as providing an extensive survey of the related biology literature. So in this case, when the mutation rate is large and the selection parameter is small, we can think of the fitness of an individual as changing over time like a random walk. So the fitness of the individual changes as different mutations appear, and so it's moving over time like a random walk. And because there are many different mutations, each of which has only a small effect on fitness, this random walk should be well approximated by Brownian motion. And as I mentioned at the end of the first lecture, we're going to approximate this population model by branching Brownian motion with an inhomogeneous branching rate. So the branching rate will depend on the location of the particle to model selection so that fitter particles are more likely to have offspring. Now, this case in which mu_n is large and Sn is small has also been considered extensively in the physics literature. Simring, Levine, and Kessler considered this case in their 1996 paper. And more recently, Neher and Halischek provided a very thorough analysis of this model. And they concluded that the fitness distribution of the population evolves like a traveling wave whose shape can be described in terms of the Airy function. I also want to mention these two other very long and sophisticated papers, one by Fisher in 2013 and one by Melissa Good, Fisher, and Desai in 2021. Those authors were interested in studying intermediate cases where the selection is not quite strong enough to fit into the assumptions of the work of Desai and Fisher in 2007, but was stronger than the regime considered by Neher and Halischek. So in the last few minutes today, I want to describe the derivation in the physics literature for why the Airy function describes the shape of the traveling wave in this model. And then next time we will see how to get this result mathematically in the setting of branching Brownian motion. And so here I'm really following the presentation of Neher and Halischek. So let's suppose that Q of xt denotes the density of particles with a fitness of x at time t. And of course, that's not precisely defined, but it's nevertheless useful to consider. We're going to let m of t be the mean fitness of the population at time t. And then the time derivative of this density Q of xt is given by the sum of these two terms. So the first term accounts for the branching, because the fitness of a particle, the rate of increase for a particle at x is the difference between the fitness of the particle at x, which is given by x, minus the mean fitness of the population, which is m of t. So the difference between the birth and death rates for a particle at x will be x minus m of t. And then this second term accounts for the mutations. We are gaining individuals with fitness x at rate mu times q of x minus s comma t, because each individual with fitness x plus s is acquiring at rate mu a mutation that will increase its fitness by s. And then we're also losing individuals with fitness x at rate mu times q of xt. Now let's just assume that the fitness distribution is described by a traveling wave with some velocity v. So we'll assume that m of t is v times t, and then the density is f of x minus v times t, where the function f describes the shape of the traveling wave. And we'll also change coordinates to let z be x minus v times t, so we're thinking in terms of the individual's fitness relative to the population average. Now, in this case, the time derivative of q is the derivative with respect to t of f of x minus vt, which is minus v times f prime of x minus vt, which is minus v times f prime of z. So we can rewrite this equation here with minus v times f prime of z on the left-hand side. This first term on the right-hand side just becomes z times f of z under the new coordinates. And the mutation term becomes mu times f of z minus s minus f of z. And because we want to think of s as being small, we can approximate f of z minus s minus f of z by a second order Taylor expansion to arrive at this equation here. So here's that equation again. Now changing parameters again, we can let sigma squared be v minus mu times s, and we can let d be 1/2 times mu s squared. And then a bit of rearranging gives us that z times f of z plus sigma squared f prime of z plus d f double prime of z is equal to 0. And if we write g of z as e to the sigma squared z over 2d times f of z, the function g then satisfies this simpler differential equation. And notice we have g double prime of z on the left-hand side and z times g of z on the right-hand side. And that suggests that the Airy function may play a role, because the second derivative of the Airy function is z times the Airy function. In particular, if we let g of z be the Airy function evaluated at a plus b times z, then the second derivative of g is given by this expression, and one can check that with this choice of b and this choice of a, that's exactly the equation that we derived. And that gives us this function here for the shape of the traveling wave. So that argument, of course, was non-rigorous. We just assumed at the outset that it was going to satisfy this traveling wave shape, but it turns out that it will be possible to obtain a rigorous version of this result from the branching Brownian motion context, and we will present that result as well as some other results for this process in the final lecture. Thank you.
So questions for Jason?
About the very last result, heuristics, let's say.
Yeah.
I didn't get what is the velocity of the wave.
Yes, I did not present here how one obtains the velocity of the wave. I just didn't. I didn't get into that here. I was trying to go with something simpler. My recollection, though, is that I could be wrong. Oscar might be able to say it more clearly. I think, though, that's where it gets complicated, and you have to match up two different solutions. Is that right? So there's an additional level of complexity to try to get the velocity.
Thank you very much.
No, there is no question in the chat.
I have a question. Yeah, we got a question back there.
Hi, sorry, you mentioned the infinitesimal model. The connection was just that you consider a very small effect of mutations, or there is something in the derivation of the variance and stuff like that that can be connected to the infinitesimal model? Right?
I didn't quite hear that properly. You're asking.
Sorry, for the infinitesimal model, the one from Fisher, you have an idea that mutations are of a very small effect. But there is also a connection between, let's say, the phenotypic diversity and the speed of the wave, stuff like that.
Yeah.
Is there a connection here also that is deeper than just a small effect of mutations?
So when I referred to the infinitesimal model, I was thinking of it in a fairly simple-minded way. Just the fact that the infinitesimal model is based on this idea that, that a certain trait, like maybe your height, is determined by many different genetic and environmental factors, no one of which is overly significant by itself. And so here we have many different mutations. They're each having just a small effect on fitness. So I didn't mean that there was I wasn't intending to claim a more precise connection than that.
Okay, thank you.
Maybe I'll ask one quick question, Jason. So you mentioned in all these discrete models that the accumulation of mutations is sort of beneficial. Every mutation is beneficial. Do any of these discrete models cover cases where you might have some sort of adaptive fitness valley type of situation where the accumulation is not necessarily monotone?
Yes, one can definitely study those kinds of models. One can study models with both beneficial and deleterious mutations. It also seems to be important to study models where the fitness gain that you get from a beneficial mutation is random. If you think about the different COVID mutations, some of them are bigger jumps, some of them are smaller jumps. And there are a whole bunch of other papers that try to deal with those things. Deleterious mutations, one can study that. When you have random fitness effects, that starts to make things more complicated.
But you still see traveling waves in these types of situations?
It's certainly that's certainly what is believed in the physics literature. In fact, I'm going to come back around to this at the end of the last lecture. There's a sense in which, when you're modeling by Brownian motion, it really doesn't matter a whole lot whether you're modeling beneficial or deleterious mutations, right? The difference is just a drift.
Right.
And so in that sense, there should be, particularly in this regime where you have fast mutations and small selection for each mutation, it shouldn't make a whole lot of difference. There should be a lot of flexibility there. When you start to do the regime where you have stronger selection, each mutation is having a big effect. That's when it gets a lot more complicated because you really have to track each mutation individually.
All right. Any other questions? All right, let's thank Jason again.